class. So we have a design description, and we've been asked to design a circuit that will transmit a high pulse with a duration of only 1 cycle when the manual button is pressed, and will not transmit another pulse until the button is depressed and depressed again. Okay, so this is a description of the problem we've been asked to solve. Okay, we are to design a circuit, and the circuit will transmit a pulse when a manual button is pressed. Okay, and when it will not transmit another pulse until the button is depressed and pressed again. So just as we said in our introductory lesson, we said that in any design we come out with the project description. Okay, so here is the project description that is given. So from this project description, the next thing we do is to draw the state diagram from this. So we are going to derive the state diagram from this. Okay, so we want to draw the state diagram. Okay, so we will be in one state, and I'll call that state A. Okay, that's the state when the system is not pressed. Okay, the key is not pressed. And when the key is not pressed, so at this state, if a key is not pressed, we are not going to get any output, right? And let me say that I'm using the more. We are to use the more model. Okay, so the output will be 0. So when the input is 0. Okay, now at this state, two things come out. Either it is 0 or 1. When it is 1, it means it is pressed, right? So that should take us to another state. And let me call that state B. And the input is 1. So once it's pressed, according to the statement, it said it will transmit a high pulse when the manual button is pressed. So the manual button is pressed, so it's transmitting a high pulse. So here what will be 1. Okay, now at this state, two things come to mind: when it is 0 or when it is 1. When it is 0, it means it is pressed, so it should go back to state A. And when it is 1, okay, what it means that it's still being pressed at this state, and it shouldn't give us any output. So over here, I would say it should take us to another state until it is depressed. Okay, so we are not supposed to get any output here. So here means that it is still being pressed. Okay, being pressed. Now over here, when it is depressed, or at this state, if it's still pressing, okay, it means the output should not give us anything. So the input is 1 here. But when it is depressed, it means it should go back and then start the whole thing again. Okay, so here is what? 0. Okay, so this becomes our state diagram. Okay, so we can see that, okay, let's reset it. Initially everything is set 0. Okay, so at the initial state, when the input is 0, we don't expect anything, so it should be 0. Okay, when it is pressed, it should take us to another state, and that state is where it's going to transmit the pulse. Okay, so 1 is output. At this state, if it's not depressed, the person is still pressing it, it shouldn't give us an output, it shouldn't change. So it takes us to a state where I would say here it should wait. Okay, here should be activated. Okay, so that is our state diagram. Now from the state diagram, what we come out with is the state table. So we are going to draw the state table for this state diagram. So we are going to derive it from the state diagram. Okay, so I have here, let's fill it. So at A, when the input is 0, it remains at A, right? And the output is 0. At A, when the input is 1, it goes to B. Okay? And 0. At B, when the input is 0, it comes to A, and the output is what? 1. At B, when the input is 1, it moves to state C, and the output is 1. At C, when the input is 0, it goes to A, and the output is 0. At C, when the input is 1, it remains at C, and the output is what? Is 0. So this becomes my state table. So this becomes my state table. Okay. Now, at this state, remember, what we do again is to code the states in the state table. Okay, so we have to code them. And we have 1, 2, 3, 2 states, 3 states, right? If you recall, we say that if I have, let's say, M state, okay, then the number of bits n. So I have 2n should be greater or equal to what? To m, right? And 1, 2, 3. So 2 to the power 2, which will be 4, right? So we have 1, 2, 3. Because it's 3, I'm going to use 2-bit representation. Okay, so the coding, so let's say coding, right? I'll represent A with what? 0, 0. B with 0, 1. C with 1, 0. Okay, so this is how I'm going to do. So let us draw the table again. Now we are going to fill in with the codes. Wherever we see A, I put 0, 0, B, 0, 1, and so on. Okay, so we are now going to change it, right? So we have 3 inputs. So A, so let's say 0. Okay, so let's do it. So when the input is A is 0, 0, right? So 0, 0, and the input is 0. The next state is A, which is what? 0, 0, and the output is what? 0. Okay, A, 0, 0, B is what? 0, 1, and the output is 0. Here is what? B, which is 0, 1. When the input is 0, it goes to A, which is 0, 0, and then the output is 1. At B, 0, 1, when the input is 1, is C. C is what? 1, 0. And the output is 1. Okay. At C, C is 1, 0, 1, 0. When the input is 0, it remains at what? Am I right? 1, 2, 3, 4. 1, 2, 3, 4. Okay. So C is 0. When the input is 0, is A, 0, 0, and is 0. Now at C, 1 0, when the input is 1, is what? C. And C is also what? 1 0. So here is 0. Here, don't care, okay, because we are not going through that state. Okay, so this become my state transition table. Okay, so that is the state transition table. Now at this state, okay, it is important to draw the theoretical model, okay, of your design. And remember, we are using the more. Okay, so I'm going to draw the more, how the design is going to look like. Then we'll continue. So this is what more is saying. We have this. We have two flip-flops, right? A and B. So you can use one block, or I'll use two blocks. I will use two blocks, okay, but you can use one block. No problem. I would. Okay. Now, here is my combinational logic. Okay, this is my memory. Okay, so let's say this flip-flop A and then flip-flop B. Right. So here, there, from here, it goes here. This is my combinational logic, and the output is taken from here, which is Y. Okay, now I have my input, which is X here, and then my feedback, okay, so okay, if I like, I can put all this in one block if you like. So this is one block. Okay, good. So this is my memory. This becomes my next state. Right? And then this becomes my present state. Okay, here become my present state. This is my output. Okay, so this is how my design is going to look like. Remember, we are using the more, and with the more, the output is controlled by the present state. Okay, so what do we do next? We need to determine the type of flip-flop that we are going to use in our memory, or to use as our memory. Okay, so I think I'll use the D flip-flop. Okay, so type of flip-flop, I'm going to use the D type. Okay, now having been able to see how the design is going to look like, and then selected the type of flip-flop, we need to modify the state transition table again, okay, to include a column for the flip-flop, and then from it we derive our input and output equation. Okay, so that is what we need to do. So I'm going to redraw the state transition table again to include the character the D flip-flop. Okay, so all I'm going to do is to transfer this here. Okay, so I have 0 0. Okay, So we have this from this. What we now need to do is to fill the column. Okay, so to fill the column, remember we've decided on a D-type flip-flop. So what we do is that in order to let me come out with the transition table for the D flip-flop. Okay, so this is my D. So for a D flip-flop, when the present state is 0 and then the next present state is 0, D is 0, right? When it's 0 and then it means the D input is 1. Whatever is D is what moves in. So here will be 0 and here will be 1. So we are going to use this to fill here. Okay. We are going to use this to fill here. Now, so QA, we are going to do for DA. We are going to use the present state and then the next present state. 0, 0 is 0. 0, 0 is 0. 0, 0 is 0. 0, 1 is 1. 1, 0 is 0. 1, 1 is 1. Don't care, don't care. Okay, let's do for DB. Here. 0, 0 is 0. 0, 1 is 1. 1, 0 is 0. 1, 1 is 1. Oh, sorry. 0, 0 is 0. 0, 1 is 1. 1, 0 is 0. 1, 1 is 1. 0, 0 is 0. 0, 0 is 0. Don't care, don't care. Okay. Okay, so we'll be able to fill the columns. Okay, the next thing we do is to derive the input equation for the flip-flop. So flip-flop input equation. Okay, now how do we do this? We do this by simplifying this using a Karnaugh map. Okay, we have 1, 2, 3 inputs, 3 input. Note our input is here, so we have 1, 2, 3. Okay, so let's solve the Karnaugh map. QA, QB, X. Okay. 0, 1. Okay, so let's fill in for. So we want to find for DA. Okay, 0, 0, 0 is 0. 0, 0, 1 is 0. 0, 0, 1 is 0. 0, 1, 0 is 0. 0, 1, 0 is 0. 0, 1, 1 is 1. So 0, 1, 1 is 1. 1, 0, 0 is 0. 1, 0, 0 is 0. 1, 0, 1 is 1. 1, 0, 1 is 1. Here, don't care, don't care. Okay, so let's circle. I think we can solve for this one, and then we can do for that one. Okay, so what will be our DA? Our DA will be equal to, if I take this, okay, it's going to be QA. I'm taking this QA, this cancel this, okay, X plus, when I take this cancel this, QB X. Okay, so that will be for our DA. Let's do same for DB. Okay, so let's do, we are doing for dB. So 0, 0, 0 is 0, right? 0, 0, 1 is 1. So 0, 0, 1 is 1. 0, 1, 0 is 0. 0, 1, 0 is 0. 0, 1, 1 is also 0. So 0, 1, 1 is also 0. Okay, 1, 0, 0 is 0. Is 0. Okay, then 1, 0, 1 is also 0. 1, 0, 1 is 0. Here is don't care, right? So we can circle this. Okay. So we can say that our dB is equal to QA bar, QB bar, and then X. Okay, so we are left with the output equation. Now, from the diagram or from the table, you see that, let's come here. Our output is depending on only the present state. So we are not going to consider the input. Okay, we are not going to consider the input. So if I'm not considering the input, it means my output will be determined by what? QA and QB. And when you look on it, we have only two states, right? Okay, and at each state, when QA is equal to 0, 0, 1 gives me 1, 0, 1 gives me 1. So I can say that my output is equal to, that is QA bar QB plus QA bar QB, right? But per De Morgan's theorem, we can say this is equal to what? QA bar QB. Okay, so this become my output equation. Okay, so what are we left for? We are left to draw the design. Okay, we draw the circuit that we are going to implement. Okay, so we draw the circuit, the design. Let's do the design quickly. Let's do the design. So we have two flip-flops, right? DA and DB. So I have DA and DB. Okay, so let me call this flip-flop A and then flip-flop B. I have my D input here, this DB and this DA, right? I have my output QA, my output QB. Okay, so let's see what's the input to DA. DA is QA, DA. So now we can do something here, right? So DA, you can factorize X, QA plus QB, then get X. Okay, so we can use this. So I have QA and QB. So I have QA coming here, AND gate. So QA go to an AND gate. One input is X, and then the other is OR gate. Which comes here. Okay, so here is this, and then I need to bring QB. So let's say this should be for QB. Okay, now let's do for DB. DB is Q bar QA bar QB bar X. Okay, AND gate. So let me put an AND gate here. Now this will be my Q bar. Okay, so this QA bar, QB bar, it's a complement, you know that. So I have my QA bar coming, so this should come, here, and then I have my QB also coming, or let S come. S should come first. I want to be neater. So S comes in, and then QB bar. Also comes in. Now we are left with the output QA bar B, right? Okay, QA bar B. So this is my QA bar, this is my B. This is my B, and it's QA bar B, QA bar B, and gate, right? So this is my Y. Okay, so it's a free flop. Don't forget your clock. So this come and join it. So this is my clock. Okay, so this becomes our design. We've been able to implement the design. Okay, it is so simple, right? Okay, so we have a reset. Okay, we can put the reset if you like. So this will be my reset. The reset to be here, the reset to be here. Okay, so that is the design. Okay, so that is the design. So in brief, from the problem description, we're able to come out with the state diagram. From the state diagram, we obtain the state table. We assign codes, and then we redrew the state table. We draw a theoretical design to depict the Moore. Remember, from the beginning we said we are using the Moore model. So here is it. We decide on the type of free flop to use, and then we came out with the D free flop transition table. So this D free flop transition table, okay, or the characteristic equation transition table. Okay, then we generated the state transition table to include the free flop input. We minimize using the input, the kind of map for the free flop input equation, and then we determine the free flop output equation, and finally we're able to come out with our design. Take your time and go through, and we will meet again. Bye bye.